But at the very least, Monday, I'll tell you if we're meeting in the classroom or if we're meeting there, and we'll do some sort of exercise where you have to receive and clear an alarm and understand the procedure that tells you how to check if it's over or under specification or what the issue is. So it'll be good. But today, we're going to talk about equipment control.
Bad for them kids over there. What kids? Oh, is that loud?
Why was he yelling at her?
Somewhat normalcy of individuals teaching.
I just think we don't have learning.
Never did.
Yeah, I almost feel bad for him now because it might have been way too hard on him. But no, I don't think that.
All right.
What I saw the video.
Everybody online, can you see those slides?
Yep.
Awesome. Okay. So we're going to talk about why we have equipment control systems, how we implement equipment control, and the operator responsibilities in interacting with this. A lot of the ultimate responsibility for equipment control lies with the management that implements the system and the engineers that are actually the cognizant system representative. However, there are quite a few things that operators are required to do and understand when it comes to interacting with that regulatory requirement and then the actual physical system. So, essentially, the regulatory wording is that personnel having operating responsibility should have simple and direct access to current status information for important systems. And important, that could mean that it's important to safety. It could mean that it's a system important to production. So it doesn't have a safety function, but if we don't have this steam generator, we're not producing any electricity, right? So it's important to production. Or it could be important, meaning current operational evolution. So things that are happening right now that are important because it's something different than is the norm, okay? And it also can include systems that are pretty minor, except that they're very expensive because they're specialized, right? So certain pumps, certain backup systems, they might be somewhat minor, but the replacement costs are major. The grates, essentially, that hold fuel in the fresh fuel storage areas, they are not going to be terribly important because you could store them in the casks as you wait. You could store them in a lot of different configurations, but you have that's designated for your storage, and replacing it because it's entirely custom would be very expensive, right? So they can have minor importance, but be very expensive, or they're important because of safety, production, or current abnormal evolutions that are happening. In this language, notice that it focuses on you as the operating personnel having simple and direct access to current status. So that doesn't talk about you having access to control of those systems, right? It says you have to understand their current status and condition. However, in the workplace, we can't guarantee that you have any information about the current status unless we have a system to control that the equipment status doesn't change from what you have verified or have reported, right? So in meeting this regulatory requirement, this standard, we have to implement a system control program. Effective control of equipment and systems requires clear lines of responsibility and authority. This is where we get the fact that we have to designate a cognizant system engineer, okay? During the operation of any facility, process, or project, there must be one individual with whom resides the responsibility for operational control and authority for changes in status of equipment and systems. So when we're talking about actually using the equipment, you as the operator are the one person who can do these things. The engineer can't come and operate your system. This is you. The engineer's authority is going to be different, and they're going to be the only person that gets to authorize changing that system, making replacements, doing certain substitutions for maintenance, things like that. But when it comes to operation, this is your authority. The engineer doesn't come in and actually turn the valves or push the buttons. You do. And you do that understanding what that system is, what that change is supposed to do, how you're supposed to authorize it, how you're supposed to report on it, and then how you're supposed to proceed afterwards, right? Usually, in order to give someone in management the actual responsibility, there's going to be a shift or operations supervisor, and then they will designate to you what specific tasks on what specific systems you're going to have responsibility and authority for, right? So you won't walk in as an operator and have responsibility for every single system, but the shift supervisor is going to decide what work package, what systems, and what operations are going to be yours on that shift, okay? And that supervisor, their responsibility is to maintain a broad perspective of all the facility operations. So all the operators going to all the different systems, they have to maintain awareness of who's doing what in what part of the facility, and then how it affects what system, and make sure that all of those groups are communicating to each other so that you don't, for example, put a system out of service to do maintenance when you're about to need that system in order to perform a work evolution, right? Making sure that meshes. Okay. It also requires coordinated operations and maintenance activities. So even though as operators, you may not necessarily be the maintenance tech, though sometimes you will perform tasks very like that, right? Just it can depend. Equipment deficiencies must be promptly identified for correction in the appropriate system. And once you as an operator identify that, you have to turn it over to the maintenance group for them to review it, schedule the maintenance, determine the post-maintenance testing that's necessary, determine what operator involvement is required, right? Those maintenance technicians and those maintenance managers, that's their function. Once you identify it, they schedule it. They determine how much of a priority it is, if it's on an important system or a safety system, they get all that worked out. But you have to communicate that to the maintenance group, right? All maintenance activities, post-maintenance testing, restoration, alignment after maintenance, even though the maintenance group is going to perform this work, they can't go do that to any system without the operations group's authorization. So that operations supervisor, before anybody gets to go manipulate a system, even for maintenance, that operations manager has to approve that work being done at that time on that system, okay? Because we have to know the status of our system at any point in time, and we have to know it's correct. If at any point during the work to do maintenance, check an alignment, do post-maintenance testing, the work either gets completed or is delayed or runs into an unexpected condition, maintenance has to let operations personnel know this. This is why a lot of time an operator will be part of the group that does the maintenance on the equipment, right? It might be the maintenance personnel identified what's the correct procedure, and they might be sending an electrician to do the lockout tag out. But a lot of times this is so closely connected with our system control and our operational status that you will be a part of these work groups very frequently, okay? Which means that when you have a system that you're responsible for the operation of, you need to be aware what is the correct and normal lineup. how should this system normally be? And when you're done with maintenance, did you really make sure that you went back and checked that it's in the right position? Did the procedure make sure that you verified that, right? You should understand how alignment changes based on modes of operation. Sometimes pumps and valves will be open or closed based on what you're trying to accomplish, right? So you need to understand how these scenarios play into your actual system so that when abnormal or emergency condition arises, you have the knowledge of exactly how that system is. You have confidence that your status information is correct, that it's been put back in its correct mode, or you've been notified of the deviation, so that all of your operational decisions can be based on current knowledge of system status, right? This is exactly what caused 3 Mile Island to have a meltdown. The operators assumed one thing was happening when it was not. And they based all of their decisions on the assumption that the piece of equipment they thought was reading a certain way was, when actually they were getting a bad reading. And if they had bothered to check the other parameters, they would have known that. But they didn't. They checked one point of information. They made all of their decisions based on that bad information. Okay? In order for you to have consistent, correct, current information, there's going to be a program of documenting, updating, controlling, and verifying all of your system statuses, okay? And it has to be implemented throughout the entire facility. It can't just be some systems. It has to be all of them. Now, some of these status programs need to be more rigorous, right? Our pressure vessel, even though it's very important to safety, does its lineup change? No, it's a giant steel tank and it remains a giant steel tank, right? So we don't need to go verify every hour that we actually have the information on our lineup correct, right? Maybe every 6 months, we just go walk around and make sure we haven't discovered some corrosion or stress cracking or connectors that are starting to degrade, right? We're not going to go walk that every day. Definitely not hourly or shiftly or something more frequent, right? Giant steel tank is assumed to still be a giant steel tank. More delicate systems that are also safety related, like your control rod drives, you're going to need to be checking those all the time, right? You're going to do a test to verify their response before every single time you start up the reactor, always. And you're going to have to shut down in order to do rod drop tests periodically to make sure that we don't need it right now, but if we were operating and they had to drop in a certain amount of time, will they? We're going to prove that they will, right? So the control of that system is going to be very involved and require constant testing and monitoring. So you can have different levels of rigor, but you still have to have system control across your whole facility, okay? Documentation for this is going to include checklists, logs, status boards, or some combination of these, right? Every control room ever is going to have at least one status board. And all of the systems that have a technical safety requirement associated with them are going to have the status of their ability to meet that technical safety requirement on that board. And if for any reason a required safety requirement, sorry, that's a bad way to say that, a system with a safety requirement associated with it cannot meet that required level of performance, you're going to be in a different mode of operation. You're going to have something bypassed. You're going to have a lower power that you can go to. You're going to be not allowed to start up. Whatever it is, your status board. Which means then there's a tremendous amount of procedure associated with updating your status board, right? Not just any person can go in and change the status board in your control room. Technicians who are coming to report something like that tell an operator, and they can update their status board. Or you have a procedure that says only the person who just signed off the maintenance can actually go change that status board, right? It's going to be controlled in some manner, very specific, okay? So what do we use these for? Checklists are going to be appropriate control documents for establishing correct component position and using them as guides when placing systems and equipment into service or other modes, right? So essentially, your startup procedure at your reactor is going to have a checklist that you go through and you verify each one of the parameters that you need to. Once that's signed off, you take that to your operations supervisor or your shift supervisor. Then they say, yes, you checked everything. Yes, it's in the parameter. Sign it off. Okay, you can go ahead and start. You're going to have a pre-startup checklist that you're going to do every time, right? Status boards are usually going to contain some sort of graphic or schematic representation or a list of system components that you need to be able to quick reference, okay? It may be things that when they're tagged out of service and repaired over a shift or outage periodicity, you're going to put that system status there and you want all of them to be back in operational mode before the end of the outage. You might have different alignments for different modes and you need to indicate what mode that system is in, right? ATR has 4 loads that can all have different experiments and have slightly different parameters, which means that you can have pumps in one part of the core running at a different speed than pumps for the other part, right? You can have your control rods in banks at different levels and have different power in the different quadrants, right? Just depending on what experiment they want to do. You're less likely to do something like that at a commercial reactor because they want to be uniformly at full power as much as possible, right? And they're really good at it. Nuclear energy has a 94% capacity factor, which means 94% of the time when we need nuclear power, those power generators are running, right? You don't do this as much with commercial power, but there may be times, and in experimental reactor operations, you'll do this a lot, okay? Frequency for performing or verifying system alignment depends on the level of control required. We talked about this a little bit, but essentially, if the system has minimal impact and is maintained in a steady state, you're not going to check it very frequently. System that undergoes frequent changes is going to have more frequent checks. And regardless of how often you normally check it, most equipment is going to require, at the very least, you check it after maintenance or testing activities. Because typically, we take that equipment out of its normal operating status in order to do a repair or a test, right? So we have to verify that we put it back how we need it before we have to rely on it, right? So more or less checking depending on the kind of system. Usually at a minimum, you're going to need to do a system alignment after maintenance, okay? So it should kind of flow obvious that if before we put equipment back in service or require it as an operator, we're going to need some sort of control to actually authorize the work to be done, right? Work authorization is going to deal with a myriad of safety issues. It's going to be given credit for dealing with our RAD, our lockout, tagout, our confined space, our heights, whatever other industrial or human safety issue might be involved in that work. But it's also going to prevent anyone from making an unauthorized change in your facility because you can't go perform work without a work authorization. This is why it's so important as an operator that you don't have the attitude, I am aware of how to do this job, I don't really need the procedure. The procedure isn't about your ability to do the actual skill or job, right? You are going to be trained professionals who will spend a lot of time having as mentors show you what to do on the job. You're going to be very good at it. The procedure is part of the work authorization that ensures the entire facility is complying with the system control program. And once that procedure is verified, everyone else in the facility who may not be as familiar with the process you're about to do understands exactly what you're going to do. And then you take that procedure and you make all of them sure they're comfortable with the equipment status by saying, I will only do exactly what's in this procedure at the time it states and with checking off these prerequisites. So even if you do a procedure so often that you have it memorized, you still do the work to the procedure because this is part of our required control of system process. Okay? One of the things that those procedures are going to ensure is that we understand if we're working on a safety system that has the potential to impact safety limits or technical safety requirements. And it tells us ahead of time what local alarms will activate and what responses we should see. This is really important because if you ever condition yourself to not respond to alarms like you should, you're entering a very dangerous space as an operator, right? You should always respond to alarms as if they're real. Except when you have a procedure that tells you you're going to receive one because you're doing a maintenance test on your radiation detector and you're going to hold a source right next to it, right? Of course, you'll get a radiation alarm. You're checking to make sure that you do. So you can then announce to everyone around you, don't respond to this alarm, and you can perform that test without responding, right? So you always need to make sure that you understand these impacts in every procedure and work evolution you do, okay? So we talked about how each one of those is going to be part of our work authorization. Everybody in the whole crew that touches that system has to buy into this process. Not only does engineering have to make sure that they understand in the design of the interconnecting systems and that system specifically, that one, they've given you a good procedure to actually test the requirements, but two, they've made sure that you know how to line it up so you don't cause an unexpected consequence in a system further down the line, right? Maintenance has to know that they can't go touch a system until operations tells them they can. Shift supervisor has to have this big picture of everyone who's working at one time on a facility. Operators have to understand why they're using a work authorization, what maintenance has just done to their system, what engineering requires the specifications that system stays in are, right? And then, of course, you're going to have various other technical experts. You're going to have criticality safety subject matter experts. You're going to have chemical safety experts. You're going to have electricians and all sorts of specific experts who may be required to get involved, as well as your safety authority, so your kind of your internal regulator that's part of the company, and then your external regulator, NRC or DOE. They also have to trust that if you have a procedure that says something is authorized, it doesn't matter if they've never seen it done before. That procedure is approved and that's the process your company used. They don't get to tell you how to do work, right? And that's something, in my experience, regulators really struggle with. They have a way that they did it when they worked, that they want everyone else to do it because they're familiar with it. But regulators don't actually get to tell you how to operate. So everyone has to buy into this, okay? So that entire work package, that authorization, it's going to put together all of the approvals, the behind the scenes data, and then that's going to feed into the actual instructions for what you're going to do. We're going to go a little bit more in depth specifically on procedures in this class. You're going to actually follow some. My plan is to have you follow a reactor startup procedure and start up the simulator reactor and go through that just step by step, following each piece of the procedure. But right now, just understand the reason ultimately that at your far end of this process, you follow a procedure is that as you trace this process all the way back, it is to give you a safely operating facility and current correct information on those system statuses. Okay? You don't have an accurate picture of the current facility status, none of your decisions as an operator will be based on truth. And then you're just guessing, right? We don't want that with our reactors. So, operator responsibilities. Were you asking a question, Jack? It has your little square highlighted.
Nope, I don't know why that is.
Okay, we'll ignore it. All right, so biggest thing, I believe that we've talked about this. I'm sure Mike talked about this in your first semester because he was huge on this. You don't work around system control processes. You don't work around procedures. You don't work around the work authorization process. Even if it hampers work completion, even then, even if doing the paperwork means you don't get the job done that day or that shift, you wait for the process to be correct before you do the job, okay? Even if it seems redundant. I had one group already review this and sign off on it. Do I really have to wait for another group, especially if that group is known to be slow? Yes, you really do. Even if you don't think it's the most effective process, you are certainly welcome to give feedback. This is a very simple task with low risk. Can we streamline it? That's a really good question to ask. But if the answer is no, this is our process, you can't work around the process. Okay, that's just one of the things that we accept in the nuclear industry, because the consequence of adding in any risk is that the public is so averse to risk. What we're going to do is we're going to end up with a situation where nuclear is not going to be an industry that the public trusts anymore. Even though we're so safe and we have such an excellent safety record, the public has no tolerance for even the smallest risk in what they already are very afraid of because of lack of knowledge, right? One of the things that's important, and you will be kind of trained on this in your facility, we don't treat safety systems like other systems. There is going to be an additional layer of rigor and burden on the control of safety systems. And if you are in any way changing or modifying or getting unexpected results from a safety system, it is almost certain that the cognizant system engineer, that CSE, is going to have to be involved. So this is a relationship that you as an operator, especially if you interact with safety systems, so if you're a control room operator or if you're a facility operator that's assigned a safety system, this person needs to be your very good friend. They need to trust your operational feedback. They need to believe you when you say, I've been operating the system and it's been slow or it's been rattling. You need to trust them that they want to make sure that that system is doing the right thing and that they're going to be looking at the data you provide and that they're going to have a plan for troubleshooting or repairing, right? So the operators and the CSEs, you guys need to be pals. Yes, Kyle.
You said something that's gonna help me remember something else, but you said safely operating a facility and
Control document, ensure that we're safely operating the facility because they give us an accurate picture of the current facility status.
and then what's CSE stand for again?
Cognizant system engineer. It also stands for like 4 other things. Crit safety engineer, and there's a few others. I was a crit safety engineer and a cognizant system engineer. I was both. So be aware it stands for multiple things. But when we're talking about system control, it's the cognizant system engineer. Okay. And this is just kind of the did you make the right choice in life? You're going to be frustrated about this process. This isn't the job for you because this is how we do business as nuclear professionals. Okay? They're not just paperwork. They are a value-added process because we have to make sure that we get that current, accurate information. And this is the best way that we have been able to implement to do that across entire facilities, across multiple work groups, reliably and effectively. Your reading in that black and yellow book talks about the fact that 30% of nuclear incidents occur during maintenance activities, where only about 2% occur during operational activities. And that's because of exactly this system being challenged. Multiple groups are looking at multiple systems, they're doing their own work. They're going out and they're changing status. And if they don't all communicate to each other and across the systems well, you're going to have an incident. You're going to have something that doesn't get done right, or there's going to be something that's a precursor to an accident. Something doesn't get shut off before work is done. Maintenance is going to be the time that this structure struggles, which is why you have to view this as an important system you have to buy into, not just paperwork that interferes with your ability to get your work done efficiently. Does that make sense? Joe?
I have a couple questions.
Yeah.
Would you call the Davis-Bessie incident as something that happened during maintenance or during operations or neither?
I would probably call that one neither. There is some maintenance issue, right? In that whatever they were doing with their water chemistry, and when they needed to be checking that, they were out of the specification that was going to help inhibit that pitting corrosion, right? So they missed some maintenance stuff. As that corrosion was going on, there should have been indications as they were operating, right? Their pH should have been changing. They should have been seeing corrosion products. The demineralizer and deionizer would have been working harder, right? Even though it's pitting corrosion and it's not as broad as general corrosion, there were going to be some indicators, right?
And there probably were, and they were covered up probably. Okay.
And they would have been small, because like we've talked about, one of the big concerns with pitting corrosion is you don't get as many indicators as general corrosion, right? It's in that little tiny hole. But there would have been still a little bit of information that they had that, well, my deionizer system is burning up faster. My zeolite beads need to be regenerated more often. So there's something going on, right? They also, I believe, falsified inspections. And so now we've kind of gone over into the whole other scenario, right? That is such a cultural problem with how they were operating that facility that there was an engineer who was willing to essentially lie about his or her control of that system. So like that's now not operations fault or maintenance fault. That is, this plant management has completely stopped prioritizing safety over production, right?
Yeah.
So I would call that, because it wasn't caught when it should have been because of that. So I would call that a complete safety culture breakdown.
My other question was about your workarounds. Obviously it happens. People do these workarounds, then they get caught probably. What do they, how do they justify that? Like, in order for that to keep happening, then somebody would have to justify it. Even if they got in trouble, they'd have to say, well, dang it, I did it because I had to. And so it keeps happening here and there. I don't know what my question is. It's like, what are they thinking maybe? What are they really thinking since you've
So
seen it?
as a regulator, I saw three main things that kind of cause workarounds to happen. One is occasionally you get people who do not have the correct mindset and personality to work in the nuclear industry. They come from an industry that is far less rigorous on their safety, and they say, this is ridiculous. Why are we being so cautious? I have literally done this a million times without checking this, without someone watching me, without a step-by-step procedure, right? So a huge example, INL is super, super cautious about its work with live electricity. You will see stuff at all sorts of other industrial facilities that people do without injuring themselves regularly that is completely disallowed at the INL, right? And so a ton of people will think, oh man, I'm going to go work at the INL, or I'm going to go work at the nuclear power plant in my city, and it's going to be super steady, and I'm going to get paid well, and I'm going to get good benefits because they're huge, good companies to work for, right? It's a great industry. And they'll bring that attitude from their coal facility or their chemical facility or their agricultural job, and they won't be able to adapt. And so they have that mindset that it's acceptable to work around because they've been a 20-year electrician and they know what they're doing. And they don't see that it's not about reflecting on their ability to do the work. It's about this big picture of the whole facility, right? So that's one. And typically those people don't last very long, right? You have an incident, and if in that review, which we're going to talk about how we actually do accident investigations and the correct conduct of ops for reviewing things that occur. If that person doesn't acknowledge that that was the incorrect way to do it, they don't typically last, right? I willfully made this decision and I'm going to make the decision to work around again. You're not gonna stay employed at a place that has a regulator that watches that occur, right? The second is that we're working with facilities that may have very, very old parts, right? They may have been built back in the 50s or even earlier. And sometimes they break down, and sometimes they're not very significant pieces, so we don't repair them like we should. I spent almost 10 years at INL trying to get one temporary mod that had been there for 25 years removed. So it had been an officially written in workaround, but it was still, we don't have the correct system to do the procedure, so we're using this temporary one, and they did that for 25 years. At that point, you need to make that your procedure and you need to accept the risk that you're creating by having this deviation, right? You what? Or repair it, yeah. It was gonna be tens of millions of dollars, which is why they hadn't done it. But in 25 years, you can come up with tens of millions of dollars, I promise. So a lot of times you'll have that something broke and wasn't fixed correctly, and now even good operators who would not normally tolerate a workaround have been so conditioned to the fact that this is the new normal, they're doing a workaround without even realizing that that is exactly what they're doing, right? Especially if it's been semi-proceduralized. We called it a temp mod, but we just kept it for 20 years. Or, even less egregious. We called it a temp mod and we kept it for a year. Temp mods are supposed to be 6 months or less, right? Temporarily, we're waiting for a repair, we're waiting for this piece to come in, we're waiting to stop doing this process, this is temporary. If that stays longer, you've now semi-proceduralized a workaround, right? So that's the other thing I see. Old equipment, something's just broken, and that workaround becomes the new normal. And then the third is just if something was in an abnormal condition, when you come on board, and that's how you're trained to do it, that's normal to you. So you may not realize that that was a temporary workaround or an authorized abnormal thing if you were trained that that was the way you do it, right? And so then you keep that on the job training in your mind unless someone stops and says, okay, we've got to train the new correct normal, right? And so sometimes it's unintentionally because there's a training gap. Those are the three things I've seen occur. Yeah. Any questions online?
Nope, all right, see you later. That's what they said. Oh, okay.
Okay, we're gonna do a quick review. Explain in your own words, what are the two main motivations for system control at nuclear facilities? Kyle.
Status changes. So you're gonna have control of your system all the time. You watch it through, right? Status changes.
So what are the
Or is that
motivations?
not what you asked?
Yeah, what are the motivations for having that system control?
Safety.
Safety and so safe operations and
Well, I only came to one, that's something else.
Okay.
Reliability,
There.
your what?
reliability of production.
It was actually the exact two things that Kyle wrote down earlier.
Safely operating the facility and accurately painting a picture of current status.
Yeah. Your motivation is to have a current picture so that you can operate correctly and safely, right? So a correct picture so you can operate safely. If you don't have a correct current picture, your decisions will be made on incorrect information and you can't ensure facility safety, right? So our top level goal is facility safety and safe operations through current correct knowledge of our system status, okay? And that's why we have system control. Okay, a couple people online. What are some of the operator responsibilities for system status awareness?
Would it be like don't do workarounds?
Don't do workarounds?
You have to keep a professional mindset and not want to. I can't remember what I was going. Where I was going.
Is one to update the status boards?
Update status boards, yep. Keeping your logs and checklists.
How about
What about if it's a safety system?
You wouldn't treat safety systems like you treat other systems.
Right? And what's one of the main differences? Who do you have to work with on safety systems? The cognizant system engineer. Yep. Okay. That's our lecture for today. Just had theory today, so we'll be done a little bit early. Same for Monday. And then next week, that alarm response will probably take closer to the whole time. Any questions?
Why did you change today?
I went to yoga, and when I got back in the car, I dumped my water bottle on my regular clothes, so I couldn't change back.
Oh, no.
Yeah, and then I dropped a glass jar all over my shoes that was full of water. I didn't have good luck with water today.
You do yoga here